Welcome. My name is Guoliang. I'm a software engineer with over 20 years of experience. So here is my GitHub profile page. So URL is github.com/GCAO. I have many public repositories, like over 100. I dabbled into many different ideas. And the Guoliang is the one I spent most time with. So this year I have 800 contributions. A lot of them are to the Guoliang repo. Guoliang is a Homoiconic Lisp-like language with a bytecode VM written in Nim. So it has over 1,400 commits. It's a solo project and a MIT license. My message today is why the Guoliang data structure matters and why Nim is used to implement Guoliang. So quick story on why I started Guoliang. So I wanted Lisp's codeless data property, but I was never quite satisfied with lists as the medium. So the vague feeling of wanting something more expressive gradually sharpens into Guoliang data types as I work with more languages and more data format. So the influences are four. So first, like Lisp. And then also, I like the data-first design in the Clojure language. And I worked with XML, HTML, and I like the hierarchical data structure with like typed nodes and attributes. And then also when I work with Ruby, I like everything is an object idea. So I combined all of them into Guoliang, and I think it's unique. So here is the Guoliang data structure. So it's just one node with type, properties, and children. And it's the core of the language. We can see two snippets here. On the left side is a data record. On the right side is code, a class definition. So they take the same format, the same structure. So on the left side, the type, it has a type, it's a person. Here you probably don't know what this person is. It could be just a symbol, or it could be a reference to an object if this is evaluated in the context of code. And then you have a list of properties, a person's name and age. And then inside, you can also have a list of children of the person. So here, like Alice has a son called Edward of 5 years old. You can have more than one children here. On the right side, in this class definition, its type is class. Class is a keyword. And the person is actually the first child of this data. And also you have properties. Here we have one property called final, whose value is true. As you may have noticed, the location of the property can be anywhere in the Guoliang. So it can be after the type, or it can be inlined between the children. So that's the flexibility of the syntax. And I also want to stress that the type, the property value, and the children can all be anything. So that's the flexibility and the goal of the Guoliang data structure. Let's compare Guoliang with some other popular data types side by side. First, we have Lisp. Lisp has list. A list is just an ordered elements. And Lisp will require you to assign like special meanings to each position. For example, for this, the first one is the type of the list. So it's a person. And then second one is the name of the person. And the third one is the age of the person. And then you can have children follow that as well. But what's important is the position carries meaning. You as a developer have to memorize the meaning of the slots, and also the code has to follow that as well. Later, if you want to change the order, you have to change a lot of things. Second, we have JSON object. JSON object is the core, is the most used data structure in JSON. So in JSON object, you have named fields, like it's kind of a bag of fields. Like no field is more important than others. So if you want to know what type of this bag is, you have to probably add a type property, or like in your code, you just have to hard code when you receive something from this sender, you treat it as something. So that's how JavaScript and JSON works. So third, you have XML. XML, structurally, it is mostly similar to Gene data structure. So it has a tag. Tag is a string, a name of the element. And then you have a list of attributes. Attribute, it's a pair of attributes. Like you have name and value. The restriction here is the attribute values must be string. You cannot have integer or anything else. Then each tag can have nested tags, can have children. So, but like there is a restriction again. You can either have multiple child tags, child elements, or you can have one long string. Or you can probably even mix strings between the child tags. But still, you cannot have an integer or like a list of integer as children. So that's the limit. Now, as we have shown earlier, Gene is combination of all of these. Like you have type, you have tag, you have list of properties like in XML, you have children like in XML, and it's even more than that. The type, the property value, and the children can be any Gene value. So that does not have to be a string or like just Gene. So this is very powerful. And we will see later how they can be very useful when you write a program or when you transfer data. So let's talk about the features, current features in Gene. So here is just a glimpse. There are a lot more features that we did not list here, but here are the major features we want to just mention. So first, we have a bytecode compiler and a stack-based VM. And also we have a full-featured parser, of course. We have functions, and also we have pseudo macros, which look like functions, but like they take unevaluated arguments. We support object-oriented programming. So we have classes, we have inheritance, we support constructors and methods. We also have namespaces. We have asynchronous I/O with an event loop. So we support real asynchronousness. We also have actor-based concurrency. And we have a full-featured CLI. So you can use that to run, evaluate, uh, run a evaluation loop, etc. You can even compile the code. So what is still being actively worked on is a module and package system. And also we are still adding more standard libraries. And I also want to stress that Guoliang is neither a static language nor a dynamic language. So it's a gradual typing language designed from beginning. So let's talk about one of the more interesting features in Guoliang, pseudo-macros. Pseudo-macros will take arguments marked as unevaluated. So on the left side is how we define pseudo-macros. So it will take the F1 keyword. F1 keyword is used to define functions, and the macros are also defined using the same keyword. What's different is in the name of the macro, you have to put a bang at its end. So you have to put this at its end to tell this is a pseudo macro. And then you define like any other function, you take a list of arguments, and in the body of your macro, you can either directly take those arguments as data, or like you can take them as code and you evaluate them in the caller's context in the appropriate place. And you can also evaluate them conditionally. So you can skip evaluate some of the arguments passed in. So that's the power of pseudo-macro. So this is not a Lisp macros, but it has a simpler implementation and a simpler mental model. And it gets you most of the way of what macro can do. So on the right side is how like this pseudo macro is used. So you just call it like other functions. But you like as you can see the bang, you know this is not evaluated here. This is also not evaluated here. This will be evaluated by this macro based on what it based on its logic. Here is how you run Guoliang. After you compile Guoliang, you get an executable. So when you run it without any subcommands, you will be displayed with, you will be shown with this helper message. So here are the subcommands you can use. You can run, you can evaluate, you can run a repo, interactive shell, you can format code, and there are a lot of other commands as well. So now we are going to run a example. So, and here is the code. So it looks like just any other script, like Ruby script, Python script, and it even supports this cban line. When you change this script to be executable, you can run it without even using this. You can directly run this script. You can use Guoliang repo to start an interactive shell. So here is how you define a variable, and this A has a value of an array, and Guoliang has a special feature called the selector. You can use it to access internal values. So this is how you access the first element of an array. And everything is an object, so you can call method on this array. Let's also look at maps. So B is a map. You can access its property using a selector. And here is how you define functions. You use the keyword fn, and the f is the function name, and this is the argument. You can give default value to argument. So when you call with one argument, A holds the default value. And when you pass two values, so A will take the first one. So we are going to show a web demo. So the web demo source code is also in the repository. You can go take a look at the full source code. After you run it, it will start a web server, and this application can be accessed at this URL. Looks like a small but complete application, like has several different pages that can be accessed using the menu, and it has a form. You can change value and submit. So yeah, it's a sort of a complete web demo. Now let me show you its code. So on this slide, I just extracted some critical parts of the source code just to explain how this works. So first, we have modules. So this source file is its own module, and some code is not. It's either from standard library or from another module, from another package. So you have to import some members from another module. Here is how you do it. You import, and here is the namespace. GNX is the experimental standard library namespace, and then under we have HTML and we have tags, and then under tags we have individual tag like div, like HTML, like header, body, etc. And when we do this import star, we are going to copy all the members into the current namespace. I know this is probably not the ideal way, and ideally you should put the individual tag names here. But as for the brevity purpose, we just did this. And here is how you define the page function. The page function take a title and a body, and they then create a HTML wrapper around the title and the body. As you can see, we use the properties here. So like the body has property class and page. So when we generate HTML, so those will be converted to HTML attributes. So here we just show you that when you compose gene element, you are composing HTML tags. And the third, so you have some plain data here, plain gene data, like you have an array of maps. Each map, each item contains the menu item. Like we have the name and we have the price. We can map that menu into HTML. So here we map them to table rows. And then inside table rows, we have cells. So we have two cells in each row. One is name and one is price. And at the end, we join the rows into a long string that will be passed to a page. And the application itself is another function. So it takes a request object, and then we look at the paths in the request, and based on which path it is, we call different function for different page. So now we understand better what a gene is. Let's look behind the curtain to see how it's designed and implemented. So this is the execution pipeline of gene. If you are familiar with the design of Java language or like Python or Ruby or like some other languages that use bytecode and a VM, you all know how this works. But even if you don't, even if you haven't seen the design of those languages, that's fine. This is not too complex to understand. So when you have a xyz.gene source file, first thing the gene executable will do is it will pass that source. It will use the parser to pass that source into a data structure that will be fed to the compiler. The compiler will take that and compiles it into a gene GIR bytecode. GIR is just gene IR. IR is in intermediate representation. So it's a bytecode. It's pretty much just binary data. And that is fed into a VM to execute one by one. So this VM is stack-based. And this GIR code is cached on disk. So repeat runs will skip the first two steps, and the performance will be slightly better. So a key design in gene is name boxing. So every gene direct value is exactly 8 bytes packed into unused bit patterns of an IEEE 754 double 9 space. So here is a 64-digit double floating number. And in a double floating number, you have one SAM bit. And then you have 11 bits for the exponent. And then the mantissa is the 52 bits after that. And when you do number calculation, sometimes you will get not a number. And so how this standard represent not a number is they put when all these 11 digits are 1, then it's a no number. And then like the rest will pretty much be ignored because it does not make a difference, right? When it's not a number and we are not going to do anything further with it, so it's not used. But when you write a program, you can take advantage of this. So here's what we do. We save the 48 bits here as the payload, and we still have 4 bits here, 4 digits here, and we can use that to tell us what this 48 bits is. So we can use this to store integer, pointer, nil, boolean, string, and other things. And we use this to tell us what it is. Like if it's here, we can have like up to 16 different types. So now it's the segment a lot of you came for. So why I choose Nim to develop a gene. So I have 5 things I want to call out. So there are like many other good things about NIM, but I just want to call out these 5 things. So first, NIM is close to the metal. NIM code is compiled to C code, is transpiled to C code, and then C code is compiled to executable. So because NIM transpiles to C and NIM supports most of, I would probably all of the C functionality, like anything you write in C, you can probably write in NIM. So it give you a lot of power. So like all the like NAM boxing I just mentioned, and the FFI for foreign function interface, and also like I can write native functions, native functions in NIM and be able to call them from GN. All that felt very natural. Like you don't have to fight to get them to work. That's a very good feature. Uh, the more you write a low-level application like this in NIM, the more you will appreciate it. Second, so this VM, the critical part is you have a loop, and inside the loop, you will be looking at each bytecode and then dispatch to a different block, block of code. So how do you do that? That is called a dispatcher. And you want that dispatcher to be as fast as possible. So here I use one of the NIM feature computed go-to. So this will allow you to this code to be optimized to be like a handwritten C dispatch. So this is one of the cool features. And the ORC. ORC is a reference count garbage collection. So it's NIM's default garbage collection, and it's very powerful. So I leverage it, and so I don't have to write a GC for GN. So a lot of the heap located data are managed using the ORC GC in NIM. And also, I know a lot of you are already know this. The NIM is very, very expressive. Like it's a NIM code looks like pseudocode, like as you see here on the right side. This code is copied from the real source code. I did not change any of this. I just like omitted some code so that this fit in this screen. But as you can see here, this code read very much like pseudocode. And so it's very easy to write and also very easy to understand. So that's the best part of NIM. You don't have this in many other languages like Rust or C. And also, last but not least, NIM gives you, NIM provides WASM support. So I was able to compile a subset of gene into a WASM, which can be run from the browser. So this is very good because nowadays program like run in the browser is very important for some applications, and NIM supports this. So there is so much to cover, but we are out of time. So before we close, I want to stress that so no matter how hard I try, there will be pros and cons in the language, and there will be compromises I need to make. So it won't be for everyone. But even if the language never takes off, the gene data structure deserves to. So the gene data structure is type, properties, and children in one node. It has the expressiveness of XML, the homoiconicity of Lisp, and that's the bet. That's why I created a gene. So I encourage everyone to give it a try, to think about it, and also to look into the design and implementation of gene. Again, the repository is github.com/gene-lab/gene. You can clone it, build it, and then you can run the repo to play with it, or even run the WASM. So you can run the WASM build and load it in the browser. There are a few examples backed in as well. And contributions are always welcome. So feel free to fork and change. You can file issues and bugs, or you can join our GitHub discussions. Thanks for watching.